your body. Okay, so the title is Entanglement, Complexity and Frustration. So please.
Okay, thank you very much. And I would like to thank the organizers and Luca in particular for inviting me here. Today I will be talking about entanglement and some interesting links of entanglement, complexity and frustration. This is work that has been done in collaboration with a number of authors, all Italians. And, but I have to thank Kazuya Yuasa and Karol Zyskowski for very interesting comments. So let me start, and let me immediately tell you that I will be talking about a system of n qubits, so n spins, and these n spins are in a pure state. So, and I will pick a typical pure state, so I take the unit sphere and I pick a wave function of the unit sphere. I pick it randomly according to the Haar measure. And I would like to tell, before I even start, that there is no spatial arrangement, no Hamiltonian, so it's just a pure state of n spins, so there is no Hamiltonian, no notion of distance between the different spins. Okay, so I will be talking about entanglement. I will not give you the history of entanglement. It's a very interesting property of quantum states. And so let me tell you what I'm aiming at. I mean, when I take a bipartition of n spins, the dimension of I take the dimension of the space to be equal, so it's a so-called balanced bipartition. And the total dimension of the space capital N grows exponentially with the number of qubits. So this is a crucial ingredient of the theory. So complexity comes out of the exponential growth of the dimension of the space. When I compute the purity of these n spins, purity can vary between 1 over n and 1. The states that have purity 1 are factorized, and the states that have purity 1 over n are maximally entangled. So purity can only change within this range. When n is large, purity can change between 0 and 1. Okay, now I would like to look at typical entanglement. Typical means that I take the Haar measure of the sphere and I just pick one random state of the sphere. And I ask how entangled is a typical state. Well, in fact, this is a question that was asked by Lopkin in 1978, so it's already 50 years ago. And Lopkin, with a very beautiful calculation, found that the average purity of an entangled state, when I bipartition the state with a balanced bipartition, is 2 over n. Now, 2 over n is a lot, and it's very close to the minimum, because I remind you that purity can only take this value between 1 over n and 1, so typical states are 2 over n. Why? Well, this is not difficult to understand. In fact, sorry, oh, it's stuck. Okay, but let me quote, this is a beautiful paper in mathematical physics, a paper by Lopkin, and Lopkin starts with this beautiful sentence, which I invite you to read. With Lucretius, I find this whole initial state of the union is repugnant, and furthermore, a pure state remains pure. So entropy should be developed without fundamental entropy. It's a very interesting comment in it. Is it? I see, that's why. I see, thank you. Okay, thank you. Okay, so I would like to understand why are these states so entangled? Because if you have a system of n spins and you bipartite the system with a balanced bipartition, this is a random state, so you have to be very lucky in order to pick a state that is factorized. Most of typical states will be highly entangled by virtue of typicality. Since the state is typical, it will happen very seldom that the state is factorized. So it's typically entangled. That's the reason why it's intuitive. So the entanglement is so large, it's very close to the maximum entanglement because of typicality. So this is a beautiful feature of typicality. Now, there is another beautiful calculation which is related to variance. This was computed by Page in 1993, so 15 years later. And the standard deviation of purity scales like this power. Now, this is a difficult calculation, it's a scientific calculation because you have the cancellation of some terms of order 1 over n squared. And essentially, this is, I tried to summarize this in this picture here. So typical, the purity of typical state is very large, is very small, so there is a lot of entanglement. And these states are a very narrow variance. Why is this? Again, because of typicality. Because if you pick a typical state and you bipartite the typical state in a balanced way, and you pick another typical state, well, since the state is typical, things will not change much if you change the typical state. So you expect that the standard deviation will be very small, because it doesn't matter which typical state you're taking. So again, this is intuitive. There are a lot of beautiful intuitive features about typical for random states. Okay, higher moments are more complicated. They were computed by Giraud in 2007, so 15 years later, and Giraud computed the first 5 higher moments. The third, the fourth, and the fifth higher moment. So we know a lot about typical states, we know a lot of moments, we have intuitive pictures, so it's a field in which you can tell a lot of things. Okay, let me digress for a minute. I will talk about an ideal gas. So, an ideal gas, I have several pictures that I picked from the internet about an ideal gas. What is an ideal gas? Well, one thing that you can tell about an ideal gas is the distribution of the velocities. This is typical in a way. What does it mean, typical? It means that if you change the temperature, the distribution will change a little bit as a function of temperature. And I would like you to ask the same question for entanglement. So if you pick a gas and you ask what is the distribution of the speeds of the particle in the gas, the distribution of the velocities will follow a very precise statistical law. Okay, and it doesn't matter if you change the container, or if you change, if it's a different kind, if you pick different kind of molecules, it doesn't matter. I mean, essentially, this is characterizing the state of the system as a function of temperature. Temperature is the only Lagrange multiplier that tells you how the system behaves. In thermodynamics, if you pick a random box and you want to find the velocities as a function of temperature, this is something that you can do. And now we would like to pick a random state on the unit sphere and define the distribution of the purity of the eigenvalues of half system. Okay, so n is going to be large, so I'm going to apply the same argument that I applied for typicality when I pick a random box. Since the state is random, it is going to be very unlikely to find a distribution which is different from the Maxwell distribution. In exactly the same way, if I manage to find the distribution of the eigenvalues of the random state, it's going to be very unlikely to find a distribution that is different from the distribution I'm going to find. Okay, there is a beautiful notion, it was introduced by Sinoletska, Zitskowski, and Plus in 2002, and it's the idea that there are iso-entangled manifolds in the Hilbert space. So you take the Hilbert space, and you look for those manifolds of states that have the same purity, the same amount of entanglement. We do not know the geometrical features of these manifolds. These are very complicated, but we know that there must be manifolds of this kind. So you change the purity, and you, by changing the purity, you can look at the whole Hilbert space of states. Okay, this is just a picture. We do not know almost anything about these manifolds. I would like to ask, what is the typical distribution of the eigenvalues of the reduced density matrix on each manifold in exactly the same way as when I ask what is the distribution of the velocities of the molecules in a gas. Okay, so you see, purity is the same, it's going to play the same role as temperature in a gas. Okay, I will not give you details, but if you massage the problem long enough, you find an equation. By solving the set of point equations, you find an equation which looks like Dyson's equation of 1962 for the eigenvalues lambda of a typical system. I will just give you the what we call the potential. There is a repulsive two-dimensional Coulomb term, and there is a harmonic potential here. So you see, you have a harmonic potential. The eigenvalues can only be between 0 and 1. 0 is the thermodynamical limit because this is 1 over n. And there is a hard wall on the left because of the positivity. The eigenvalues cannot be negative. And there is a hard wall on the right because of the unit trace condition. They cannot be larger than 1. Okay, so the problem I have to solve is to find the distribution of these eigenvalues in this potential with these two constraints. Interestingly, this gives a Tricomis equation. This equation that I'm writing here, P is the principal value. It's an interesting, beautiful, very simple equation. I have to solve it for rho lambda, and the solution are known to be in a compact support for Tricomis equation. And let me give you the solutions. When purity is small, I remind you that 1 means here 1 over n. I'm rescaling the eigenvalue by multiplying them by n. So if purity is small, this is the minimum allowed value, 1. If purity is small enough, the distribution is a semicircle, which is a beautiful result in itself. I remind you that there is an n factor missing here, so there is a bigger semicircle. If purity is a little bit larger, between 5 over 4 and 2, by the way, 2 are the typical state. 2 is 2 over n, so it's the value of the typical state. So the typical state are exactly at this point. The distribution is Marchenko plus 2. So it's a deformation of the semicircle. What happens is a very interesting mathematical phenomenon. You have the semicircle. At some point, the semicircle will touch the boundary. On the left-hand side, will touch 0, and it develops a singularity, which is integral, of course. It grows like the square root of lambda did. Okay. If purity is even larger than 2 over n, so we go to the other side, 2 over n is the typical state. If I ask that the system has even more entanglement, so if purity is larger than 2 over n, eventually I will go towards the factorized states. The factorized state, when I diagonalize the density matrix, will look like this, 1 and all zeros there. Okay? And purity will look like this, and there is one eigenvalue that evaporates out of the continuum of the sea of eigenvalues of order 1 over n. Let me tell you, this is an interesting conclusion in itself. Let me explain it to you in simple words. You take a system of space, you bipartite it, and you demand that purity is finite, say 0.32. Finite means not order 1 over n, 0.32. So you may wonder, if I bipartite the system and purity is 0.32, how many Bell states are there going to be in the system? Not really Bell states. How many very entangled states are there going to be in the system? Only one. Only one. Not 2 or 3. You see? So you bipartite, you demand that purity is 0.32, and purity is 0.32 because of one entangled state. Not 2 or 3. This is a consequence of thermodynamics, but I don't want to linger on these ideas. Again, it's intuitive, but intuition, you have to build up an intuition, which is not always easy sometimes. So, okay, by the way, there is a phase transition of first order here, because there is a gap. There is a gap here, and this is, the gap is a cost. So I tried to summarize what happens here to entanglement. So purity is between 1 over n and 1. These are very entangled states here. You have a first phase transition here. You have typical states here. You have a first order phase transition here, and then one eigenvalue evaporates to infinity. So we have the whole picture. The whole picture. By the way, for those of you who are interested in gravity, there is a metastable branch. So the two lines branch off at the typical state. There is a metastable branch, and this is a theory of gravity. I have no idea why it's a theory of gravity. I'm not an expert of gravity, but it is a theory of, sorry, two-dimensional gravity. It's related to tie links. So it's interesting that, there is a theory of gravity when you study entanglement. Okay, so this is a picture. I try to summarize what happens with the entanglement of a bipartite system. Now, what I told you so far, you have n spins, you bipartite and balance bipartition, but in a sense you are fixing the bipartition. You have many states, many typical states, according to the hard measure, but you are defining entanglement according to a given bipartition. Now, I would like to talk about multipartite entanglement, and I think I want to skip, I want to be fast. So there are a lot of interesting ideas. I would like to characterize multipartite, and I need statistical methods. There were a lot of seminal ideas in this context from the early 2000s or something. What I will do, I will look for entanglement when I take a system of n spins and I change the bipartition. So I will pick all possible bipartitions of the system of n spins. Okay, great. Okay, so let me start from a simple example. You might think that this is, I don't want to say a trivial problem, but a problem which is easy to understand. It is not. It is not. And let me give you an example. First let me define. So you see, the way I define the cost function, which is going to be Hamiltonian for me, I take purity, and I average purity over all possible bipartition, over all possible balanced bipartitions. So this is my definition of bipartite entanglement. Sorry, the notation is a bit heavy. It depends on the number of spins, it depends on the wave function, and I call it multipartite entanglement. It's simply the average of purity over many bipartitions. Oh, since purity range between 1 over n and 1, the average purity will also range between 1 over n and 1. It inherits the same bounds as the purity of the single bipartition. Okay, so now let me tell you what happened. Take a pure state. What I told you is only valid for pure states. I will not talk about mixed state. So take a pure state of the whole system. You have complex coefficient and you have normalization. The potential of multipartite entanglement, what I call the multipartite entanglement, is a complicated function of, is a complicated quartic functions of the coefficients. The quartic function is complicated. I wrote it explicitly here to give you an idea. It's something that you have to look at, either numerically or analytically. You have to try and understand what happens. In a sense, the entanglement of the wave function has become a classical field theory of the coefficient of the complex coefficients of the wave function. There is no quantum anything anymore. I'm studying a classical field theory. Okay, frustration. I give you a very quick introduction. Frustration in humans and animals arises from unfulfilled needs. And Freud related frustration to goal attainment and identified the inhibiting condition that hinder the realization of a given objective. This is the first time frustration appears in the literature. In the psychological literature, there are many definitions, but roughly speaking, if I have to summarize from a physicist's point of view, A situation is frustrating when there is a physical, social, conceptual, or environmental obstacle that prevents the satisfaction of a desire. Interestingly, definition of frustration appears also in the jurisdictional literature, and it's related to an increased incidence of parties ceasing to be excused from performance of their contractual obligations. The first example I find is from 1956 in an Australian court. It's interesting if you read it. So here, essentially, they say that, of course, whenever the law recognizes that without default of either parties, a contractual obligation has become incapable of being performed because the circumstances in which performance is called for would render it a thing radically different from that which was undertaken by the contract. In summary, it was not this I promised to do. So this is frustration in law. You see, you would like to do something, but you're not able to do it anymore. And then, you know, by the way, in 1956, in this district council, people were not, what do you say, sent to jail? They were not sent to jail because they said, well, since you were not able to fulfill the contract, but you wanted to, I will not send you to jail. I wonder when this would be valid today in Italy. Not anymore, probably, you know. If you cannot do it and you promise, you go to jail anyway. Okay, frustration. Frustration. This is the average purity over all possible bipartitions, and I would like to ask, can I saturate the lower bound? If I cannot saturate the lower bound, I will say that there is frustration in the system. In the following sense, take n equal 4, only 4 qubits, not infinity. I bipartite the system according to a given bipartition, the red bipartition, and I ask that purity be 1/4, which is the minimum possible value. Can I do this? Yes. I can find a state for which purity is 1/4. Now I take another bipartition, the blue one, and I ask that purity be 1/4. Means that each bipartition, this is bound by 1/4. So each bipartition should be 1/4. Can I do this? Yes, I can do this. Now I change the bipartition again. I take the last bipartition. Can I ask that purity be 1/4? No, I cannot do it anymore. So already for 4 spins, there is a competition between the different bipartitions. 2 bipartitions can saturate the lower bound. The third one cannot do it anymore. So you see, I call this frustration. You would love to satisfy the other bound, but you cannot do it anymore. Okay. This is what happens when you have 7 or 8 qubits. It is interesting. I said I would not talk about applications because the audience is theoretical physics, but let me tell you one application. So I told Luca that I would not be doing application, but I will do one application. So you see, here you take purity, 7 qubits, there are 35 bipartitions, 35. So you take a state and you design the state in such a way that you satisfy that purity is minimal, so you have a lot of entanglement for bipartition number 1, 2, 3, 4, 32. Up to 32 bipartition you can satisfy the bound. Then you are not able to satisfy it anymore. So frustration arises at the very end of the process. 3 out of 35 bipartition cannot saturate the lower bound. When you go to 8 bipartition, this is done numerically. The situation is a little bit more complicated. You can saturate a number of bounds, but then frustration explodes at the very end. This is not satisfactory. Usually, when you have frustration, this is a called K-SAT problem in statistical mechanics. When you have frustration in statistical mechanics, you are not happy when frustration appears at the very end of the process. So the best way to avoid this is to ask random questions. Rather than starting asking questions, the two of you, I ask random questions to random couples in the audience. If I pick random bipartitions, randomly extracted partition, frustration is born at 2/3. I don't know whether 2/3 makes any sense. We were not able to do the calculation for 8 spins. We will in the future. We will do it in the future. But I'm not able to answer this question. So you see, this is a typical phase transition for a complex system. There is a critical value of the parameters, the fraction of possible answers to the questions you ask, and in this case you said you can satisfy 2/3 of the answers when you extract the bipartition randomly. Okay. Okay. Let me summarize again. Before I summarize bipartite entanglement, for bipartite entanglement, when I fix the bipartition, I know exactly the distribution. Once you know the distribution, you can compute all moments. All the calculation by looking, by page, by Giraud, the first moment, the second moment, the first 5 moments, they are a consequence of the exact distribution if you manage to find the exact distribution. Here, I'm trying to summarize. This is done, it was done in a beautiful paper by Scott in 2004. So, the number of qubits, if the number of qubits is 3, 4, 5, 6, can you, the existence of a perfect nest means that I have a perfect maximally monopartite dynamic state, meaning that I can saturate the lower bound for all possible bipartition. For 3 spins I can do it, for 5 spins I can do it, for 6 spins I can do it, for 4 spins I cannot do it, it's what I showed you before in the slide. For n larger than 7 spins, I cannot do it. So there is frustration. In fact, the number of spins for which there is no frustration are special cases, 3, 5, and 6. Scott understood something important. Completely independently, long before we published the paper in 2008, and this was done in 2004. So he understood that you can have perfect codes. Codes is when you have they are called quantum codes in quantum information. You can have perfect codes. In other words, you have a code that is shared by a number of parties. For example, 3 parties, 4 parties, 6 parties, and so on. If the number of parties that share a code is 3, 5, or 6, then you can have a perfect code. You can actually encode the system in a perfect way. This is quantum communication. If the number of parties is 4 or larger than 7, this perfect encoding of information becomes impossible. This was the Scott understood this, and then Ziskowski and collaborators, Gonieske, Latorre, and other people, they don't talk about nest state, they talk about AME states. But if there are questions, I'd be happy to answer them. Now, this is interesting because there is no way of encoding information in a perfect way if the number of qubits is almost anything besides special case, 3, 5, and 6. And you may know that there is a quantum computer in Naples. I was involved, it's done by Francesco Tafuri. The group is amazing. Young people, all young people, perfect gender balance. I love electronics. Some of you may not like electronics. I love electronics. So if you ask about electronics of the system here, they are all very happy to answer. And each answer, in 30 seconds, you understand what's going on. So it's a beautiful group. So I'm happy to, I advise this group, these are all the official ceremonies when we open the computer. So far the computer is 48 qubits. They will extend it to about 100 probably in the next future. There is going to be one in Salerno, by the way, as you may know. We are thinking of bridging again. We cannot compete with IBM or, this is impossible. So I suggested they do something slightly different. I will keep this suggestion for myself. But essentially, assume that you have a computer in which the architecture, the qubits have a given architecture, for example, on a square. In practice, it becomes very difficult. It's easy to control 2 qubits if they are close to each other. If the 2 qubits are at the opposite side of the matrix there, it can be very difficult to bridge information between these 2 bits. Therefore, if you think about a perfect code, you might not be able to correct all mistakes. Maybe you can correct mistakes if the two qubits are close to each other, but it's more difficult to correct for mistakes if the two qubits are far apart from each other. Do you agree? Because that's why you have to take care about how the electronics is built up. And then it becomes crucial. If you have a quantum code with 4 qubits, you have already an interesting application. There are mistakes that you might be able to correct for 2 qubits that are close to each other, but not for another bipartition of the 4 qubits, if you see what I mean. These are 24 qubits minus 2, 25 minus 2, say 23 qubits, but the number of logical qubits is less. You know, it's not 23, it's like 3 or 4. So you would like to check for mistakes, and you make error correcting codes, and it becomes crucial to understand which errors you can correct and which errors you cannot correct, not because you are not able to correct them in principle, but simply because the qubits, the architecture of the qubits is complicated. This is an immediate application. I'm always doing theory, but I put my H bars and C's back into my equations at the end of every calculation. I'm always amazed by the fact that such an artificial idea like, not artificial is the wrong term, such an abstract idea like multipartite entanglement can have an immediate application in a quantum computer. Okay, so we were all very happy with this. Let me give you a bit of thermodynamics before my chairperson becomes nervous. I have the partition function. I built up the partition function with a cost function. This is the Haar measure, uniform, and I introduce an inverse temperature there. There are different regimes. When beta goes to infinity, you have the minimizers of the Hamiltonian. This is what I call the mess, because you have a lot of entanglement in the system by simply taking beta to infinity. When beta equals 0, you have typical states, because the way the cost function disappears, you simply have the random system. Thermodynamics is like pork meat, nothing is thrown away. So you take beta to minus infinity, you go to negative temperatures, and you get separable states in one shot, let me say. So just one parameter, one Lagrange multiplier, and you can study minimizers, maximizers, and everything else. I will conclude with this one. It is very difficult to perform analytical calculation. You have to look at the Feynman diagram of the expansion. It's not simple. However, the average purity scales like 2 over, I use a different notation. This is the 2 over n, what I called 2 over n before. So the average purity is easy to compute. When you look at the second cumulant has a coefficient which is transcendental. Transcendental coefficients are very rare in statistics when you look at phase transition in statistics. If the partitions were independent, this would scale like n to the minus 3. So the fact that this is minus 2.41 detects the fact that the bipartitions are not independent. It does not detect frustration, but it's the path leading to frustrations. The third cumulant, the skewness, is even more complicated, and again it's a transcendental coefficient. So there is a lot of interesting stuff to be understood. I don't give you other thermodynamics. Let me tell you just something. The number of states in the Hilbert space grows like terrible. For 10 spins is 10 to 307. So we simplify the problem. We take plus or minus signs rather than complex coefficient, plus or minus signs, and we can count the states. So by doing simulated tempering, this is due to Giorgio Parisi, not to me, we can count the states. For you may wonder what are the number of, for 5 you have no frustration. You can count the number of perfect codes. And for 5 it's 4,547. So the Hilbert space is huge. It's 10 to the 21 or something. So you can count 5,000 states out of 10 to the 21. So we are on the way to understanding more and more. Maybe if you reorganize the conference in 1 or 2 years, I'll be able to tell you a little bit more. Thank you very much for your kind attention.
you have a question?
Hi, thank you for your talk. I understand that your results are dependent on the potential that you showed right in the very first slides, right?
So, yes.
Yes, so I wonder if this potential is unique.
Is what?
Unique. Are there other possible potentials?
Good question. No, it's not unique. You can define multipartite entanglement in many different ways, and this is related to the occurrence of frustration. Let me make an example because to give you an idea can be a bit complicated. You may ask, given a K-SAT problem in statistical mechanics, this is becoming classical statistical mechanics, you may ask that frustration appears at the very end of the process. If you want such a definition, then you have a unique definition of multipartite entanglement. That you may ask a different question. You may want that multipartite entanglement does not depend too much on the bipartition. Then you are minimizing not purity, but the standard deviation of purity. You agree? Because you want that the multipartite entanglement does not depend too much on the bipartition of the number of spins. If you try and define multipartite entanglement by demanding that the bipartition is not very important, then you have a different definition of multipartite entanglement. So depending on what you want, you are in a sense free to choose multipartite entanglement in a different way. I'm not answering your question. Even if you ask me a specific test, is this definition unique? I don't know.
Thank you.
More questions? I have a question
yeah,
actually
please.
regarding the last slide that you are mentioning.
This one?
Yes, this one. So this means that in reality the number of optimal codes is possible to get it. And up to how many qubits you can get it?
7.
And that's it.
That's it.
Okay.
But we are working to, let me say, since you asked this question, thank you very much. The number in purple here, Paolo Scarafili and Giorgio Trott are two students, a PhD student and master course. They are extremely good, both with numerics. I'm amazed how good they are with numerics and things. And I asked them to the objective is to arrive at, say, 12 qubits. So far 7, but the problem with 12 qubits is that you can go, the thermodynamics limit is always easy to do, well, easy in a sense. Sorry, there are slides I didn't show. Look at the numbers. It's really complicated. Really complicated, but maybe 12 qubits is still feasible. It would be good to have codes for 12 qubits.
Yes,
it would be very good.
Yeah,
very good.
about 7.
Yeah.
Okay. Thank you. Are there more questions? If not, let's thank again
Thank you.
Professor Pascazio.